Hello, welcome back. I would like to go over some of the concepts from chapter 6, which is focused on work, energy, and it's also a chapter that's focused on oscillations, although we won't go into that as in much detail. The more important concepts from this chapter are the concepts of work and energy. So far in this course, we have talked about describing motion. We have talked about the causes of motion, which is a force. Another way to think about causes of motion, or why an object moves in a particular way, or why a system behaves in a particular way, is through energy considerations. Um, Force is a vector quantity, so it's oftentimes very difficult to work with vectors. But what we will learn in chapter 6 is that energy is actually a scalar quantity. So we only have to deal with the size of the energy, or how much energy an object possesses, and that can often help us analyze the system in a slightly different way than analyzing it using forces. And the nice thing is we don't even have to think about we don't even have to think about the direction of the force. Okay, we can just think about how much energy does this thing have, and how does that energy transform as this object moves, or as this system evolves in time. But to first think about energy, we have to think about the connection between work and energy and forces. Okay, so let's kind of tie the two chapters together first, and then we can kind of move forward from there. Now, in physics, like a lot of the other things that we've talked about in this class, in physics, the concepts of work and energy have very specific meanings. So let's first kind of conceptualize what is work and what is energy, and then we'll quantify it using the mathematics, and then we'll solve some problems using energy considerations. So let me share my screen. I'm going to bring up my whiteboard, and we'll go over the concepts of work, force, and energy. So the simplest, hold on. Why is my tablet not? There we go. Okay. The simplest example I like to give to help us think about work and energy is the idea of a water wheel. In the past, people often used water wheels to power a mill, for example. Um, so let's just suppose here's the water wheel, and there's a stream of water that comes in, falls over the water wheel, and the water wheel turns, and it can either grind up flour or do something else, whatever it is, okay? So the water flowing in, initially it has some amount of energy, okay? I'm not going to say how much it is, okay? I'm not going to put a number on it, but let's just say the water has some energy to it, okay? It's moving. It's also at a certain height above the ground, so it has some energy associated with this. When an object possesses energy, that means it has the ability to do work on something. Okay? So in this particular example, the water has energy, and that means that it has the ability to do work on the water wheel and turn the water wheel. Okay? So we would say that as the water moves over this water wheel and turns it, the water does work on the water wheel. The energy from the water is being used, and it's doing work on the water wheel. Therefore, the water wheel gains that energy. okay? Because the water is now doing work on the water wheel, and the water wheel gains energy because it's now moving and spinning. Now, once the water falls over the water wheel and turns the water wheel and falls, down, the water has now less energy at the end. Some of the energy that the water had went into turning the wheel. So we can see that these concepts of energy and work are very intimately tied together. If an object has energy, it can do work on a system. And when an object does work on a system, the system gains energy. Okay, so they're very much tied together. So how can we define what is work? Okay, and in everyday life, we say work is like the job that we go to. We do work, we do outside work, we do yard work. But in physics, again, work has a very specific meaning. In physics, work, which we will denote as W in our class, is equal to force that you apply on an object multiplied by the distance that the object moves. Okay. So this is the connection between last chapter, which deals with forces, and this chapter, which deals with work and energy concepts. So here the water does work on the water wheel by pushing it. There's a force that the water exerts on the water wheel. That water wheel moves distance d. There's work being done here. Now, work, so it's a force times a distance. So the units for work are the units for force is a Newton, and the units for distance is a meter. Those are our standard units. A Newton meter is also known as a joule. That's another way to say Newton meter. Joule was a scientist who investigated energy and work, in particular with relation in thermodynamics, but we apply this name for a Newton meter. We name that unit a joule. For reference, 1 joule is about the energy that an apple has. So an average sized apple, 1 meter above the ground, that apple possesses 1 joule of energy. Okay, so 1 joule is not very much energy. So work is a force times a distance. When I do work on an object, I've added energy to that object. So simple example, if I pull a crate across the floor. So let's say I'm exerting a force this way on the crate. The crate moves a distance d. Am I going to be able to just multiply the force times the distance in this case? We have to be careful with work because work, how do I change? I guess I can't. Oh, yes, I can. We can't just multiply by the force times the distance here. We have to take into account one more consideration in that the force and the distance have to be either parallel or perpendicular to each other when you multiply them here. So I need to take this component of the force, which is parallel to the distance that the object moves, and that's the work that's done here. The component of the force that's perpendicular to the direction of motion, so this part of the force, by component, I just mean part. So this part of the force that's pulling like upward is the part of the force that's perpendicular to the motion, right? The object's moving to the right. This part of the force is pulling up on the object. This part of the force is pulling to the right. Only this part of the force, the parallel part, contributes to any work done. So when you're solving problems, trying to solve for work, make sure that you multiply by the force times the distance, and these two have to be either parallel or anti-parallel. This part of the force is not adding any energy to it, right? It's the object is moving to the right, so it's gaining energy, and its motion is to the right. This part of the force is not adding to the energy in that sense. Okay. Another thing about work is that it's a scalar quantity. I do not have to define a direction of work. I just have to tell you what is the size of the work done. So it could be 10 joules, 20 joules, whatever. Just a size, no direction needed. Just size or magnitude. So that's how we define what we mean by work in physics. And this has a few applications for things like simple machines. So there might be a few questions in your homework about simple machines. Simple machines are machines that amplify the force. Okay, so what do I mean by that? So let's take a simple machine, a lever. Okay, a lever is one simple machine. And let's suppose I, put the lever, let's put the fulcrum right here. And I want to lift a big boulder with this lever. Okay, very massive boulder, so it's got a huge mass. It's going to take a lot of force, therefore, to lift this thing up. So the force to lift this thing up is needing to be very large. So I need a really big force. What a lever does is allow you to apply a smaller force on this side. So I got a little force on this side. Okay, to be able to lift this boulder. Okay. So I only have to input a small force to be able to lift a large force or force of gravity over here. Okay, but what's the difference between these two sides of the lever? Okay. On this side of the lever, I have to push down very far. Right? I have to push down a very big distance d. I'll make this big D. And as you can imagine, on this side of the lever, the boulder is not going to lift up very much. It's only going to go up a small amount, little d. So there's a trade-off here. I have to apply a smaller force over a larger distance to be able to lift a larger object with a large amount of force over a smaller distance. But in both cases, the work input here, remember, work is force times distance. Okay, so on this side, the work input is a small force over a large distance. The output work done by the lever is a large force only lifting up a small distance, d. And what you will find is that the work in is always equal to the work out for simple machines. Because you always have this trade-off between force and the distance. The mechanical advantage of a simple machine is how much the force is actually amplified by. So if I put 1 Newton of force in applied and I get 10 and I can lift 10 newtons on the other side, the mechanical advantage is 10 here. Okay, but what is the same here is the work input and the work output. That's always the same. Same thing with pulleys. You can use a pulley to lift a very large object, but you have to pull the rope much longer, length, and the and the box, maybe only lifts off the floor a little bit. Um, Same thing with like your bike, for example. When you change gears on your bike, the force that you have to apply to the pedal is smaller, but you have to pedal a lot more times to get up the hill. So there's always a trade-off, and the work that's input is always equal to the work output. Okay, so I'm gonna, oh, and one more thing before I move on to energy concepts. Work can be a positive or negative number. Okay? So if I drag this thing across the floor, I'm doing the force is parallel with the direction of motion here because it moves this way. So I'm doing positive work on this box. Right? Now, what would happen if I let go of the box and the box gradually slows down and stops? Why does the box slow down and stop? Because there's a force of friction opposing. So force of friction opposing the motion, it gradually slows down and stops. While the object is slowing down and stopping, let's say it moves a distance d. Okay, so it's still sliding to the right, but the force of friction is slowing it down. The work done here would be negative because the force and the motion of the object are opposite. And so instead of adding energy, remember, because if I do work on something, I add energy to it. So in the case of dragging the crate across the floor, I'm adding energy to the crate. So energy would be positive here. If I release the crate and then it slows down and stops, in that case, the force of friction is doing negative work on the crate. It's removing energy from the system and slowing it down to stop. Okay. So work can be positive or negative. Okay, but the positive or negative here does not refer to the direction. It just refers to whether the work is adding energy to the system or removing energy from the system. So that's kind of the concepts of work and how we can apply it to simple machines. Now let's think about the connection between work and energy. Okay. For the example of dragging the crate across the floor, if I drag the crate across the floor a distance d, you said that the work done is the force multiplied by the distance here, where the force is the parallel component of the force. We said, hey, this thing is going to add energy to this crate, right? The energy that it adds by doing work on this crate, the energy that it adds is, so the work done on the crate, or the box, whatever you want to call it, is equal to the change in the box's KE, or kinetic energy. It makes sense. If I do work on an object and I drag it across the floor, it's going to pick up kinetic energy. It's going, and what do I mean by kinetic energy? Kinetic energy is the energy associated with motion. This could be the motion of a macroscopic object like a box. Even the molecules in your body have kinetic energy associated with them because they're vibrating. Okay, so kinetic energy can span huge range, and quantitatively it is equal to 1/2 mv squared, where v is the magnitude of the velocity of the object, m is the mass. I won't derive the steps here for why the work done on the box is equal to the change in the kinetic energy. If you're curious, send me a note and I can explain why this is true. Okay, but you can just take my word for it. This is one of the main principles in physics. This is called the work energy theorem. If I do work on an object, the net work done on an object is equal to its change in kinetic energy. Change in kinetic energy, by the way, when you see change in, it's always final kinetic minus initial kinetic energy. It's always, when you see this delta sign, this just means change. It's always the final value minus the initial value. So the final kinetic energy that you can find by 1/2 mv squared minus the initial kinetic energy. So let's suppose I apply, let's make this simple here, and let's just make the force parallel with the direction of motion here. So let's just suppose I apply a force of 50 newtons on this box and it moves a distance of 4 meters. And this occurs over a time of 4 seconds. And the final speed of the box, the final velocity, magnitude of the velocity is 2 meters per second. Okay, so the size of the final velocity is 2 meters per second, and it starts from rest. So initially, the initial magnitude of the velocity is 0 because it starts from rest. What is the work done on the box? And what is the final kinetic energy of the box? The work done on the box is equal to the force that I apply on the box multiplied by the distance that the box moves, if these two things are parallel to each other, which is the case here. 50 newtons multiplied by 4 meters, that's going to be 200 joules. The final kinetic energy is 1/2 m final velocity squared magnitude. And by the way, the mass of the crate is 100 kilograms. The final kinetic energy is equal to 1/2 m, which is 100 kilograms, times the final velocity squared. Which is 200 joules. Remember, joules is the unit for work done. And since work done on the box is equal to its kinetic energy, energy also has units of joules. What was the initial kinetic energy? Well, it was 0, right? Because it was initially at rest. So the change in the kinetic energy is the final kinetic energy minus the initial kinetic energy, which is 200 joules. That is equal to the work done on the box, which is 200 joules, which is what physics, one of the main principles in physics tells us, work energy theorem. Now, there's a different type of energy that I'd like to discuss with you. We talked about kinetic energy, which is the energy associated with motion. There's another type of energy, which is the energy called potential energy. Okay? So it's the energy associated with an object's potential to do work. So, like, let's suppose I take a book. Okay? The book starts from rest, okay, on the floor, and I lift up the book and then I place it on the shelf, on the top shelf. Okay? And on the top shelf, it is also at rest. The final kinetic energy is 0. The initial kinetic energy is 0. So there's no change in the book's kinetic energy, right? I only need final and initial, right? If it's at rest initially and at rest at the end, its kinetic energy has not changed. Okay, but I've done work on the book, right, by lifting up the book, right? So what am I missing here? I apply a force on the book, I lift it up, but its kinetic energy doesn't change. I place it on the shelf. By doing work on the book, my hand lifts up the book, right? There's one more force that we're forgetting about. It's the force of gravity acting on the book. So not only is my hand doing work on the book, lifting it up, the force of gravity is doing work on the book too. Okay? And if I lift something against the force of gravity, okay, and I place it up on that shelf, for example, that means that instead of the book gaining kinetic energy, the book has gained potential energy. In this case, gravitational potential energy. So I haven't added any kinetic energy to the book, but by doing work on the book and lifting it up against the force of gravity, I have added gravitational potential energy to the book. So potential energy, or PE, is another type of energy associated with the object's potential to do work, right? Because if the book was then dropped from that particular height on the shelf, when it falls and hits the floor, it can do work on something on the floor, right? Right. It's like the water falling over the water wheel. The water initially had potential energy. It's up on like a, it's a waterfall, right? So it's falling over. Okay. So in that case, the water had potential energy too. Potential energy mathematically is equal to the mass of the object times g times h. M is the mass of the object, g is the acceleration due to gravity, which is 9.8 meters per second squared, and h is the height of the object above the ground. The g here does not need to be made negative. G can be positive because in deriving this expression for potential energy, we've already taken into account that the force of gravity is going down. Okay. So whenever you plug in the numbers for this, you can leave G positive, 9.8. And I'll put a G over here to indicate that we're talking about gravitational potential energy. There's other types of potential energy that we'll talk about, but this is the main one. Now H is the height above the ground. Well, where's ground? Okay. Ground can be wherever you want it to be. Ground is actually chosen arbitrarily. Okay. But once you choose ground level, that's where it has to stay. Okay. So you can't move it around when you're solving problems. Once you choose ground level, you have to stick with it. But it doesn't matter where you choose ground level to be. Okay. Normally, we choose ground level to be something like the surface of the Earth. Okay. But you could choose it above the surface of the Earth, below the surface of the Earth. That would just adjust the value of your gravitational potential energy. But the cool thing about gravitational potential energy is it doesn't really matter to me if you tell me something has 10 joules of gravitational potential energy. It doesn't really mean anything to me because I don't know where you've chosen ground level to be. You haven't given me a reference point. If you say this thing has 10 joules of gravitational potential energy, 100 meters off the surface of the Earth, for example, then I would say, wow, that thing doesn't really have that much gravitational potential energy considering it's so high above the ground. I had to have a reference point. Do you see what I mean? So generally, we choose height to be ground level, but you can choose it wherever you want to be. Convenient for the problem that you're solving. All that really matters is the change in the gravitational potential energy with respect to ground level. There's one more type of potential energy that's discussed in this chapter, which is called EPE, or elastic potential energy. The best example of this is the energy that's stored in a spring that has been compressed or stretched. When you compress a spring, you feel like that spring wants to release its energy. Okay? When you stretch the spring, right, the spring always wants to pull the object back into the equilibrium point, or the point where the spring is neither stretched nor compressed, right? So springs can also um, have a type of potential energy, which is, or stored energy, and we call that elastic potential energy. Quantitatively, that's equal to 1/2 kx squared. So let's suppose here's my spring, and let's suppose the spring at this length is relaxed. It's neither stretched nor compressed. Okay? And let's suppose I stretch the spring out to this point. Now the spring has some potential energy associated with it. The distance that I stretch the spring is equal to x. Okay, so that's what x means here. So that could be the distance that the spring is stretched or compressed by. That's the amount that the spring is stretched or compressed by. And k, and that would be in meters. And k is called the spring constant. Its units are Newton per meter, and conceptually, the spring constant just refers to how stiff the spring is or how stretchy the spring is. So a slinky, for example, is very loose. It would have a very low spring constant, whereas like the springs in your mattress or like the shocks in your car, for example, are very stiff springs. They would have a very high spring constant. And so they would store a lot higher amount of elastic potential energy because they're a lot stiffer. So those are kind of the two types of energy, kinetic energy and potential energy. And then of course there are subcategories within both of those. For potential energy, we're going to mainly talk about gravitational or elastic potential energy. And again, elastic potential energy, I do work on the spring. There's also the force that the spring exerts back. Okay, so there's stored energy here. When I do work in lifting something, I apply a force on the object, but there's also the force of gravity acting on the object as well, storing energy there. Okay? And in both of these cases, the stored energy then can be released to do work, right? A spring gun can do work on a bullet and shoot the bullet out. Last part of this chapter that I would like to discuss with you is very important. Okay, this is one of the main key principles that you should take away from physics, is called the conservation of energy. Conservation just means doesn't change. So, but somebody says energy is conserved. That just means that the total energy of the system doesn't change. And you've all heard this before in that energy is neither created nor destroyed, right? So whatever energy the whole universe has, that's it. So, um, you know, it's conserved. It doesn't change. If I've got 100 joules of energy in the universe, I'm not saying that's how much energy there is in the universe, but I'm just saying if there's 100 joules of energy in the universe, that doesn't change. Energy is conserved. Now, the type of energy that it is can change. right? The energy can be transformed between kinetic energy and potential energy and vice versa. But if I've got 100 total joules of energy, there's always going to be 100 total joules of energy if energy is conserved. So let's think about this. Example, go to the park. You pull your child back on the swing. Let's suppose we place ground level right here, okay, where the swing is in its lowest point. Ground level means that the height is equal to 0 meters. So you pull the swing back, okay, the child is up here. Okay. At this point in the swing, okay, the child has 0 kinetic energy, right? You've pulled the child back. They're not moving yet, right? So they're not having any energy of motion. They're just sitting there. Okay. But they do have gravitational potential energy, right? Because they are at a height above the place where you have chosen ground level to be. mgh. Let's just say that when you multiply mgh out, it gives you 100 joules. So initially the child has 0 joules of kinetic energy, 100 joules of gravitational potential energy. So their total energy, the sum of both, is 100 joules. What conservation of energy says is that for this system, the child swing, right? Whether the child is here, 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 blah, 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 blah. Wherever the child is in the swing, conservation of energy says that they're always going to have 100 joules of energy because that's what they started with. So when you get to the bottom of the swing, they have 100 joules of energy there too. But it's no longer gravitational potential energy. It's 100 joules of kinetic energy because now at the bottom of the swing, they're moving the fastest, right? And then as they swing back up, that energy then gets converted back into gravitational potential energy. And at the top of the swing on the other side, they have 100 joules of gravitational potential energy. So if they have 100 joules of gravitational potential energy over here and 100 joules of gravitational potential energy over here, that means they're always the highest they will ever go is the same as the height that they initially started with. So if you've ever seen the old bowling ball trick where somebody lifts up a bowling ball and drops it in front of their face and it swings back, it's never going to hit their face, right? Because the bowling ball can never go higher than what it started out with initially because you're not adding any energy into the system, right? The energy is conserved. So why does the swing eventually slow down and stop here? Okay. In everyday life, we know that energy, like if I pull the child back, the child's just not going to oscillate back and forth forever, right? Why does the swing eventually stop? Because of frictional forces. Okay, so there's frictional forces doing work. And in fact, those frictional forces are doing negative work, remember? Okay. They're removing energy from the system. So air resistance on the child, the frictional forces in the bearing where the swing is connected. Right? There is energy loss there. It's lost in the form of heat, right? When you rub your hands together, that's frictional forces, okay? Your hands heat up. That heat energy, it's still a form of energy. It's heat energy, okay? So the energy has been transformed into heat energy. And then it's just kind of like lost to the environment, right? We can't get that energy back. So it's not really a useful energy that we can take advantage of, right? Kinetic energy, potential energy, those are energies that we call mechanical energy. They're energy that is useful for us in simple machines and things like that. But heat energy, it's kind of a random type of energy. So once it's lost to the environment, it's very hard to get that energy back. So that's why the swing eventually slows down and stops because of these frictional forces. The total energy is still 100 joules, except now it's 100. Once the child eventually slows down and stops, that means I've lost 100 joules of energy in the form of heat lost to the environment. Okay. So energy is technically still conserved, right? But mechanical energy is not conserved. The kinetic energy and the gravitational potential energy do not stay the same because that energy is lost. But if we could negate these things, like if we could go somewhere where frictional forces were very, 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 very negligible, and you pulled your child back on the swing, your child would go back and forth forever due to conservation of energy principle. And in a lot of cases, the frictional forces are very small compared to the kinetic energy and the gravitational potential energy, so we can negate them when solving problems. Okay, so let's practice this. Let's suppose let's actually do some numbers here. So let's suppose I have a child on the swing. Let's not include the mass of the swing itself. Let's just suppose the child has a mass of 25 kilograms. And you lift up the child to an initial height above the low point of 1 meter. What is the magnitude of the velocity at the bottom of the swing? We're describing motion here. We're still describing motion, except we're using energy considerations as opposed to Newton's second law, F net equals ma, which would be very difficult to do here because the force is continually changing direction, the tension force, it's messy. Okay, so let's use energy considerations to solve this instead. When you're solving problems using energy consideration, if you want to apply conservation of energy, you have to choose the 2 points that you're comparing. Okay? So you have to determine what is your initial point and your final point. Your initial point for this problem is right up here, where he's at the maximum height above the ground. And the final point is the low point in the swing, right? So those are the 2 points that you want to compare. Conservation of energy says that the initial energy is equal to the final energy. We're going to assume here that frictional forces are negligible. Okay? So we can apply conservation of energy here. The initial point is when the child is at the high point. Okay, you've pulled the child back. This is their initial point. What kind of energy do they have at the initial point? Well, like we said, it's only gravitational potential energy. There's nothing else here. If they were moving at this point, you'd have to add that in. You'd have to add in the kinetic energy here, but there is none. The final energy at the low point. At the low point, we said now they're moving, so they have kinetic energy. At the low point, we've called that ground level. Height is equal to 0. That means they have no gravitational potential energy here. If they were still a height above the ground, like maybe this position, they have both gravitational potential energy and kinetic energy. So you'd have to have two terms here. But if I just want to know what is their speed at the low point, all I have is kinetic energy. All right, so the expression for gravitational potential energy is mgh. I'm going to put mgh initial, so I know that I'm talking about the initial point, and kinetic energy at the final point is 1/2 mv final squared. I'm looking for the speed, or the magnitude of the velocity at the bottom of the swing, which is v final. So this is what I need to solve for. Mass, which would be the mass of the child. Let's not worry about the mass of the swing itself. You could add it in, but it doesn't matter because mass actually cancels out. It's on both sides. So I've got GH 1/2 V final squared. I need to isolate V final, so I'm going to multiply both sides by 2 to get rid of this 1/2. And I'm going to solve for V final, which means I need to take the square root of both sides. And now I plug in the values. 2, G is 9.8 meters per second squared. You can use 10 meters per second squared. We don't need the negative sign here because we've already taken the negative sign into account when we derived an expression for mgh, so don't need to put the negative sign here. It's already taken care of. And the initial height above the ground was 1 meter. Notice that the final velocity here does not depend upon the mass of the object. Right? There's no mass here, which is what we learned when we talked back in chapters 1 and 2 about kinematics, right? If I drop something from a certain height in the absence of frictional forces, okay, the mass of the object does not play a role. Mass never came up in any of the kinematics equations, right? So what is the value of this? Calculator. 4.4 meters per second. If this was a real life situation in which there was frictional forces at play, the final velocity would be a little bit less than 4.4 meters per second, right? Because we'd be losing energy in the form of heat energy. That's why we have to keep pumping, right? We have to keep adding in energy. We have to keep pushing the child in order to keep them going. We add in energy by doing work on the child, by pushing them. There's energy loss in the form of heat, right, due to the frictional forces. So we push the child, continually to make up for the fact that we're losing energy this way. But in a lot of situations, the amount of energy that is lost due to frictional forces is negligible compared to the kinetic and gravitational potential energy, so we can ignore it for our purposes and to make our life easier. So that's kind of how to solve problems using conservation of energy principle. First of all, you have to identify, can I apply conservation of energy here? If there's no frictional forces or energy being added into the system, like by an external push here, you can use conservation of energy principle. Then you choose the 2 points that you want to compare, the initial and final points. Identify the kinds of energy that the object has at those points, and then solve for the variable that they're asking for. You could do the same thing with a spring. Okay, if I compress a spring by a certain amount and then I let it go, right? How fast does the bullet shoot out on the other side? That's also a conservation of energy problem. I've got potential energy being converted into kinetic energy. Okay. So you could solve problems involving potential energy too, elastic potential energy too. Um, those are the main points that I'd like you to take away from this chapter. There's also a section on harmonic motion, so oscillating systems. I would read over that because there might be a couple of questions on your homework about that, but mostly I want you to be able to solve for the work done on an object, figure out what its final velocity is, right, the magnitude of its final velocity, use conservation of energy principles to solve problems like this one, okay? But it's important to be aware of energy concepts because we know that in the news and such, there's a lot of issues related to energy and the energy crisis and different forms of energy, renewable energies, green energies. So just getting a basic understanding of energy in general is extremely useful. And we will come back to types of energy and renewable energy sources in a future chapter. Okay, so don't forget about energy. Okay, we'll still come back to it. But you want to be an informed citizen, so understanding the basics of energy and what is involved in work and energy concepts helps you do that. Okay, so I hope this helped a little bit. I hope this helps you solve your homework problems. And if you have any questions or concerns, feel free to email me. I'm happy to meet with you on Zoom. You can post in the discussion boards on Blackboard, and I'll try to get back to you as soon as possible. All right, so I'll see you next week. Bye.